Imagine a ladder standing upright against a wall. Now the ladder starts to slide down the wall, with its bottom moving away from the wall along the floor like this. Let us ask an interesting question. Somewhere on this rod, we choose a fixed point called P. The position of this point is such that it divides the rod in a fixed ratio A is to B. For example, if A and B are 1 and 1, then point P lies exactly at the midpoint of the rod, so it stays equally far from both ends. If A is 1 and B is 2, then point P is closer to the wall end and farther from the ground end. On the other hand, if A is 2 and B is 1, then point P shifts closer to the ground end and farther from the wall end. No matter how the rod moves, this ratio always stays the same. Our job is to understand the path traced by point P as the rod moves. Now, before doing any mathematics, let us think visually. As the rod moves, its ends slide smoothly along the wall and the ground, and the point P also moves in a smooth and continuous way. When P is exactly at the midpoint of the rod, this curve looks like a perfect quarter circle. But when P divides the rod in any other ratio, the path no longer looks circular. Instead, it stretches more in one direction and starts to look like a quarter ellipse, right? Now, let us try to prove it mathematically. To describe the position of point P, we introduce a coordinate system. The wall is taken as the vertical axis and the ground as the horizontal axis. The point P has coordinates x and y, where x is the horizontal distance of P from the wall and y is the vertical distance of P from the ground. So this length will also be equal to x, right? Now, here comes the nice trick. This rod makes some angle with the ground. Let us call this angle as alpha. Consider the segment of the rod from point P to the ground. This segment has a length proportional to b. So let us call it b itself. In the right triangle formed here, the side opposite the angle alpha corresponds to the vertical distance y. This tells us that the sine of angle alpha equals the opposite side over the hypotenuse, or y, divided by b. Now, consider the segment of the rod from the wall to point P. This segment has a length proportional to a. So let us call it a itself. Now, if this angle is alpha, then this angle will also be equal to alpha, because both these lines are horizontal and thus parallel, and so both these angles are corresponding angles. Now, in the right triangle formed here, the side adjacent to the angle alpha, or this one, corresponds to the horizontal distance x. This tells us that the cos of angle alpha equals the adjacent side over the hypotenuse, or x, divided by a. Okay, now what is the next step that comes to our mind? Yes, the basic identity from trigonometry, which says that the square of the sine of an angle plus the square of the cos of the same angle is equal to 1. So substitute the values of cos and sine here to get x over a whole squared plus y over b whole squared equals 1. This gives x squared over a squared plus y squared over b squared equals 1. And, folks, this relationship is the equation of the curve traced by point P, which is the equation of an ellipse. Now, if a and b are equal, we get this, which is the equation of a circle. This is why the curve looks like a quarter circle when a and b are equal, and like a stretched quarter ellipse when they are not.